Alright guys, welcome to this page of the notes, and what we're going to do now is we're actually going to do some similarity transformations. And I just want to quickly remind you of something that we've already done, and it's simply this coordinate notation for doing transformations. You should recognize this from what we did back in chapter 1, and again I will remind you of it as we go through this, right, because I know it probably for many of you has been a while. But remember the way that this coordinate notation works. What they're going to do is they're going to give you a point, an ordered pair, which is x comma y. The coordinate notation tells you what to do to each of those coordinates. So for example, if I'm going to do a dilation where k, lowercase k, is my scale factor, what this is telling me to do is multiply each, the x and the y coordinate, by k, right? So let's say, for example, let's say that k is 4, right? If my scale factor is 4, whatever ordered pair they give me, x comma y, I will multiply the x by 4, and I will multiply the y by 4, and that will give me a new ordered pair, which we designate by putting the little prime above it, right? So let me give you a quick example. Let's say that k is equal to 4, and I give you the ordered pair A is 1, 2, right? So I give you the point 1, 2. Here we go. We're going to perform this transformation. Right here is my x, y, right? There's my ordered pair. So remember the way that we did this. A is 1, 2, and then we drew that little arrow, right, to show that we're performing a transformation. Well, the transformation I'm performing is I'm going to multiply k times x, and I'm going to multiply k times y. What is my k? My k is a 4. So A prime is now going to be 1 times 4 is 4. 2 times 4 is 8. And there you go. You just performed a transformation. The original point, the pre-image, was at 1, 2. I do the transformation, and my image, right, my A prime, is now at the point 4, 8. All right, so that's the way that all of these are going to work. We'll go ahead and run through a couple of these together. Once again, reminding you that if k is between 0 and 1, it's going to shrink the size of the figure, and if k is greater than 1, it's going to make the figure bigger. We've mentioned that a few times. It's worth repeating just to remind you what the scale factors mean. Here we go. Let's do one together. I want you to determine whether the two figures are similar. Graph both the pre-image and the image. If the figures are similar, I want you, right, we together, but you are going to write the similarity transformation. So this is, well, here you go. You'll see in a second. Pre-image, image, all you got to do, plot the points. Very, very simple. Actually, here, let me do them in two different colors. I will do the pre-image in red and the image in green. All right, here we go. My first point is 0, 1. 0, 1, that is right there. My next one is 1, negative 1, 1, negative 1, and my third one is at negative 1, negative 1, negative 1, negative 1. All right, so there's my 3 points, which I have done in red. That's my pre-image. Now, the image. Plot the points. 0, 3. Right there. 3, negative 3. Right there. And negative 3, negative 3. Right there. Connect the dots. And there is my image. Okay, so now we take a quick look at it. First, is it the same shape? Well, yeah, definitely. They're both triangles. It would appear that the angle measures are the same. Of course, you'd have to get a protractor to measure them, but I'm not asking you to do that, right? They're the same shape. They're both triangles. What about orientation? Well, even the orientation appears to be the same, right? Even if I were to go, okay, this is R, and sure, I named this point X, but you could just as easily say R and R prime, could you not? Sure you could. And then S, S, and S prime, even though I called it Y, right? You could call it S prime if you wanted to. So it would appear that the orientation is the same. So what I'm asking you to do is write the similarity transformation, which just simply means, what is the dilation here? Well, it's not too terribly hard to recognize. Just look at the points, right? How do I go from 0, 1 to 0, 3? Well, it looks like I multiplied everybody by 3. 0 times 3 is still 0, but 1 times 3 is 3. 1 times 3 is 3. A negative 1 times 3 would be a negative 3. Negative 1 times 3, negative 3, and a negative 1 times 3 is negative 3. So, real quick, not hard to see, my scale factor is 3. And so all I'm doing is I'm taking x, y, and my transformation is going to be 3 times x and 3 times y. That's all I did, right? Try it, right? Here's r, 0, 1. R prime would be 0 times 3 is going to be 0. 1 times 3 is going to be 3. Is that the point I got? 0, 3? It sure is. 0, 3, right? Instead of calling it r prime, we called it x, right? So what I've got here is my similarity transformation. I know it's a similarity transformation. Why? Because that's a dilation, right? It's my scale factor. I have increased the length of all of those sides by 3. Let's try another one. Okay. Once again here, let me do my pre-image in red. I will do my image in green. And here we go. All right, 2, 2. That's easy right there. 2, 4. Again, pretty easy. That's right there. 6, 4. 6, 4. And 6, 2. Okay, cool. So it looks like we got ourselves a rectangle, and there is my pre-image right there. In fact, it is P, Q, R, and S. Oh, wait. Yes, yep, P, Q, R, and S. Okay, let's do my image. So, first one is at 5, 5. 5, 5, okay. Then I have 5, 9. All right, no problem, that's right there. I have 12, 9, 12, 9, got it right there. And 12, 5, right there. Ooh, look at that, it is still a rectangle. Okay, this is W, X, Y, and Z. All right, my job is to see, can I write a similarity transformation by this? Okay, so we take a look at these numbers and we see, is there some easy way to get to the new coordinate, right? Okay, so just looking at it, I'm not recognizing anything, but there is a way that we can check. And remember, we said that a dilation is so that the ratio of corresponding sides are always going to be the same. Well, we can check that. Here we go. Let's do side WX, which corresponds with side PQ. Right? Here's PQ. Here's WX, right? Those are corresponding sides. We can also then check side XY with its corresponding side, which is QR. Right? Here's XY, here's QR. Well, let's check and see what we get. All right. WX, 1, 2, 3, ooh, that's 4. PQ, 1, 2. Oh, well, that's not too terrible. 4 divided by 2, of course, is 2. All right, well, maybe we're on to something here. XY. 1, 2, 3, 4, 5, 6, 7. Ooh, 7 divided by 1, 2, 3, 4. Well, is 7 divided by 4 2? No, definitely not 2. Does not equal 2. And so right away, that's it. We're done. right? Because we know that in order for it to be a dilation, the ratio of the sides have to be the same. This one's 2, this one's not 2, and so no. There is no common value of K which means that there is no similarity transformation. Right? The only way that I can write this similarity transformation for a dilation is if the ratios are all the same, right? The ratios of corresponding sides have to be the same. I just did 2 ratios and I didn't get the same thing. So there's no way to write a similarity transformation for dilations if I don't have a common ratio of all of the sides. And so in this case, there isn't. It is not because of a dilation that I go from this pre-image to this image. It must be something else, which we'll do much, much later. For now, we're only interested in dilations. I have a couple more example problems for you on the next page. I'll meet you there.